construction at various stages. And actually, it was Roosevelt who was Undersecretary of Navy under Wilson, who had made sure that enough battleships were going to be built to replace all the coal burners and to make us the #1 fleet in the world. Well, when the 20s came in, the war to end all war was over, and people couldn't understand why we were spending all that money on battleships. The result was that the Naval Treaty of 1922, you had a 5-5-3-2-2 tonnage ratio agreed upon between the U.S. and Britain at 5, Japan at 3, Italy and France at 2. And so you had to get rid of your tonnage to get down to that level and scrap your new construction. Well, that treaty resulted in us not building 12 battleships, 2 of which were converted to the carriers Lexington and Saratoga, and also getting rid of some old coal burners. But we still had the most modern coal burners, about 6 of them were kept. Okay? So, come middle of the 20s, worldwide, the coaling stations were being shut down, and all ships in the world were being converted basically to oil or scrap. And this being the newest coal-burning battleship, it was the last one to be converted to oil, which was in the late 20s. And they widened the ship by 10 feet, putting in torpedo blisters. And they took out 14 coal-fired boilers that were hand-fired, required 120 stokers and coal passage, and replaced them with 6 boilers in these 3 boiler rooms that we'll be going into the middle one. The end result was that you had, by shifting to oil, you no longer needed the coal bunkers that were under this deck and under that deck there, going out to the side of the ship. All of a sudden you had all that space. And you also had a fuel that gave you 40 pound for pound, gave you a 40% greater cruising radius. 18,000 BTU per pound for oil versus 13 for coal. So it's win-win from that standpoint. But in the conversion, they also put in 2 longitudinal bulkheads in the coal and the bunker spaces, so that they ended up with 5 watertight subdivisions between the open sea and the boiler room. You had the blister on the outside for anti-torpedo. You had the old original hull. And then where the coal bunkers were, they put in 2 longitudinal bulkheads. And then you have this bulkhead, which goes down the boiler room. And you no longer had to have a big door in it to pass coal through. You could put the oil in your double bottom, which was kind of handy. This space is an ammo passage, and was in the original design and still is. On the other side of that bulkhead is a ammo hoist for 5 and 3-inch guns and powder. And then they would put them on a bucket or dolly and bring it up here, and this is the 5-inch hoist that took powder and shell up to the 5-inch gun on the main deck. The 3-inch hoist is right over there. So that briefly is what was done. But in widening the ship, they increased the displacement from 27 to 34,000 tons. Most of that weight went into a 4-inch armored deck that was put on the second deck, right over our heads here. The purpose was to explode an incoming shell. That's how the British and Germans sank each other in Jutland in World War I. The shells did not penetrate the side armor. They had learned, their gunnery had improved to the point where they could lob shells at 8 or 10 miles away, and it came down through unarmored decks. So the 4-inch was to explode an incoming shell, and these decks were increased to 1.5 inches to stop the shrapnel from going down into the boiler room. So that was the fundamental hull change to the ship. We're going to go into what they call the drying room. Above each of the 3 boiler rooms that remain, there's a space on this deck and a space above, and they're too hot for anything except to dry clothes or to store spare parts. And that's so the crew would take their laundry from the room which is on the second deck aft and would hang it here, and it'd dry real quick. But we'll go in here, there's a step on the other side, and watch out to your left, because there's a big hole that we don't in the other 3 boiler rooms, 2 boiler rooms.
So you're boiling it in the plumbing right through here?
Well, no, we're boiling it in here, right in this boiler. You said where's the water coming from, not where's the steam going. And
Now this is flame here, right? This is just flame right here, right?
in the firebox, yeah. And then, as soon as we get them down here, I'll take you quickly through it.
Mr. Gillette?
That's
you like
it,
to come
okay.
up here and all your-
Okay, let me take you quickly through the cycle. And I'm gonna start with the oil side. Over here, vertically, you see the cylinder jacketed there for a reciprocating steam pump that'll take suction of fuel oil from the tanks. And in cold weather, you have to have a recip to be able to suck it out of the tank without using a heating coil. The vertical black drum there is really an expansion dome that helps even out the pressure on the discharge side of the pump, because it's a recip that goes back and forth. The oil coming out, though, goes through a strainer and then into the heater here. It's heated up to about 90 degrees and put into a day tank, which is under main plot. You just came from
We
main
just
plot.
came from main plot, so the deck y'all
Okay.
were standing on was where
Okay.
the heated oil was stored.
Then the oil is sucked out of that tank in main plot by one of these 2 pumps here. These are centrifugal pumps. And the discharge goes underneath this grating and then up into that heater. It's heated to 190 degrees and then pulled over into this pipe here and down into this header here. And then about 80% of it or more will go right back down underneath and into the suction of the pump from which it came. Now, the whole purpose of that cycle and recycle of the oil is that on the centrifugal pump, you have a constant discharge pressure once you get above about 60% of design capacity. And if you are recycling 80% of the oil, then you've got almost a constant high pressure that can be used to atomize the fuel that is going through the other 10 or 20% of the fuel that is going through this and into the burner assembly. Now, the oil comes out through the nozzle. You've got a spray here. You've got a 2,500 degree flame. Over about a period of an hour, it will atomize or cause carbon deposits in the burner tip. So you got 2 firemen on each boiler. One fireman has sight glasses here. When he sees a poor flame pattern, he'll crank open the valve on one of these other burners while pinching down the valve in this one. And then hopefully with gloves on, he removes this.
What kind of gloves?
Huh?
What kind of gloves?
Gloves. And,
What kind of gloves?
yes, but,
Asbestos gloves.
oh yeah. We didn't worry about those things back then. Okay, so here's the jig. The spares are here. that he could do. And then what he did is take off this tip assembly.
It's hard to get that back.
You're sure you follow underneath that grate, it's gonna be bad.
Yeah, we don't, in fact, I just happy just leaving it there so people can see it. If you look at this, you'll see there's offset grooves. You see those offset grooves? That causes that disc to spin as the oil goes through. That gives a pinwheel effect to the spray and gets good mixing for combustion in the firebox. Now, let you put that back on.
Sure.
Okay. So we've got 2,500 degree flame here, and the gases are going to go either way, and then up into the ductwork you saw above.
Okay.
If you look inside here on the sides, you'll see 2-inch diameter screen tubes that are heavy walled. They can take the radiant heat of the fire. But once the gases get past it, they get down to 1,900 degrees, and then progressively are cooled down through this generation tube down to about 480 degrees. Now I say 480 because steam at 300 pound pressure in this boiler boils at around 450. And you can get within about a 30 degree approach temperature. When you're firing this boiler with 1 or 2 burners, which causes me to explain that this boiler is totally oversized for the service. It was taken off of one of the ships that was scrapped pursuant to the Treaty of 22. Had already been built, so when they replaced the coal boilers, they had plenty of room. They were replacing 14 boilers with 6. And these had much higher capacity to begin with. So don't think this is typical of any World War II vessel boilers. If you go on one of the big battleships, they would put out 200,000 horsepower, whereas this one had 28,000. And they would do it with the same space about. And they're 4 boiler rooms that you have here in these 3 boiler rooms. So if you do visit Alabama or the Missouri and so on, you'll note the difference after seeing this. This is 1920s technology. And of course the engine room is 1910 technology. I guess you can't go down there right now, but I like to tell people that the only other engine room like that is on the Titanic. Good luck.
Port side is open, very stormy.
Okay, good. I would say this is so oversized that firing with two burners, and normally that's all you needed for this ship to cruise 10 knots. And that, in World War II, that's all she did. She was with convoys, or she sat off Iwo Jima and lobbed shells ashore. This is only the fast World War II battleships that went with the carrier task forces. So the exit temperatures would go up probably 700-800 degrees if you fired all the burners. And that's why in World War II they output what they called economizers, 2 bundles in the uptakes. Because the temperature was higher, they wanted to get the heat efficiency, and they used that to preheat the feed water. And just to give you a little bit of marine engineering, you can only get 10% of the energy that you put into boiling a pound of water. You only get 10% of that back in an engine. The rest is rejected to seawater. Or you can increase the efficiency to 20% by using the exhaust steam to heat the feed water that's going to the boiler. Now the World War II vessels all had superheaters. And then that, you take the steam, saturated steam at 450 degrees, and you heat it up to 850. And this was built in the 20s for a superheated ship. With superheat, that energy that goes in raising it to 850 is 100% recoverable, except for friction. That is why a turbine drive could get you 30 to 35% thermal efficiency, whereas this ship had only 20%. Makes a lot of difference in fuel consumption. Nowadays, you don't make steam plants anymore, except on shore power plants. The manufacturers of slow-speed diesels will guarantee 50% thermal efficiency. So every commercial ship, I don't care whether it's a passenger ship or a container ship or whatever, it's diesel-driven. Navy ships go to gas turbines, but that's for military reasons. Okay, that's a little bit of an aside, but hopefully it helps understand what we have here. I would also explain that normally the way you would operate is one boiler on the line in each boiler room. The other might be hot and ready to come on, but there'd be one on the line. And yet, if you think that you need 28,000 horsepower for 20 knots, which was max for this vessel, cruising, it was 10 knots. That's what convoys did. You need only 1/6 of the power when you are going at 10 knots. So you divide 28,000 by 6. That says you need, say, 4,500 per boiler room. You can do that on one boiler with 2 burners. So this had a lot of spare steam generation capacity, but you didn't have an engine that could use it, is my point. Okay, other details. If you look in there, you see fire brick that's black. Fire brick should be sandy colored. Well, when this ship went into Todd Galveston in 1990, we were underwater here. The water level, you can see right up there.
Oh, yeah.
Okay, right there. And so this was because when they brought her down in 48, they had not sealed off the sea suctions and discharges. It wasn't the hull that was leaking then, it was the piping systems. But the water in here had oil on top of it, and that's what coated them. People ask, and I tell them that it takes about 10 to 12 hours to bring a cold boiler on the line. If you bring it on too fast, the fire brick will just start peeling away, spalling, because it expands so slowly. So it's essential that you treat it with respect. Once you get it hot, you want to keep it hot, because then you can fire as much additional fuel in it as you want. There was a man beside the fireman I mentioned here. There was another fireman on each boiler who could stand over here and get wall-eyed looking in these 2 periscopes. His job was to keep the captain happy, because the captain didn't want to see you making smoke. If you made smoke, you were wasting fuel. And yet if you had too much air and no smoke, you were wasting fuel. So the way they do it is this guy would pinch down on the air until this guy saw smoke. And then you'd back it open just enough to get rid of the smoke. And you could not get below about 10% excess air beyond theoretically required for combustion without making smoke. That was the gold standard in the Navy at the time. Another very important thing was water quality. You had to keep the pH, alkalinity, within a very narrow range, about 9.5 pH, so that the carbonates that you cannot keep out of the boiler feed water would precipitate out like the little snow that you get in a children's Christmas globe, you know? It would precipitate out in the system, settle in the bottom of the water drum here, and then you would periodically open up the valve on the bottom of the drum and blow it out. The standard was 1% blowdown. That meant for every 100 pounds of water that was boiled, went to the engine, and came back as water, you'd blow down about 1 pound. 1 pound in 100. If you got outside where you should and you got scale forming on the inside of the tubes, then you'd get a hot spot, and then the tube would blow. And then you'd have to shut the boiler down, drain it, let it cool a little bit, and then some poor bastard was going to have to go inside here with an expansion tool and plug off the leaking tube. And he'd have to go up into the steam drum up there and do the same thing. And they do that 100 times. You've got 700 tubes in there, and they're not going to take the boiler out of service for 3 or 4 months to retube the boiler. They just plug it off. So hopefully during the life of the ship, they never replace the boiler. They just plug off a few tubes. But that's why you had a man full-time doing nothing except testing water quality. And what do you use to get the alkalinity? Just old soda ash. Let's see. Another man was full-time up there. Nice warm job. He didn't have to do much. He just had to watch this gauge glass here and make sure the water level in the boiler was in the middle. Because if the water level ever exposed the tubes we've been talking about, they'd melt, and then you're really out of business. I've seen it happen one time in my career. The main, I mentioned the fuel pump. This is the main feed pump. The guy up there would control the amount of water that was put in to maintain the level in the steam drum. And unlike everything else which is in duplicate in the boiler room, that fuel pump and this pump are all by themselves, but they're cross-connected with the other 2 rooms. So that pump there and this pump here can supply all 6 boilers with fuel or with water if necessary. So that's how it wasn't depending on this single one. It's a massive manifold back there that cross-connects into the other rooms. This boiler was designed for a ship, I said, with superheater. This is the connection for the superheater, but they don't have one because it's a reciprocating steam engine. Instead, they use it, and when nobody was looking, they could open the steam valve, and they could rotate a slotted pipe in here so that steam spray would blow carbon off of these tubes and get better heat transfer. Of course, you do that at night, nobody looking.
Because all that stuff's going out the smokestack.
Other minor details. Here's a drip pan that used to be under here because when you take the burner tips out, inevitably there'll be a little oil spilled. You could start up the cold ship here because they have a emergency generator topside, and it'd make enough power so this pump could put kerosene in there, and you put a rag on a long pole, a metal rod, and light off kerosene. You have to get the boiler fire break reasonably hot before you can sustain combustion on the heavy fuel oil. Any questions? Am I a good talker, or what am I missing?
You're a great talker.
One other thing I'll mention, since he hasn't stopped me yet.
We're a little over.
Yeah. Up here are large steam mains. It's called a ring main. That steam main goes through, on both sides of all the boiler rooms and the engine rooms. And basically, they're cross-connected, cross-short so that any one boiler can be isolated from the rest and supply the engine room. So this, again, redundancy in case of damage is a prime consideration in boiler or, let's say, machinery design in a naval ship. Put it that way. I guess that's about it, unless I got some people asking me questions.
Well, Tom, as always, thank you.
Well, I have one.
Yeah.
Okay, you said 10 to 12 hours to get a boiler online. What about the main engine? How long did you have to do something to repair that?
Well, what when you're down, you're usually bleeding steam into the jacket on the engine to keep it warm. You don't start up that engine cold, I'll tell you. I frankly don't know how long it takes, because normally there's always one boiler on the line keeping it warm. You have a jacking engine also. You have a jacking gear on it that rotates maybe 1 RPM or something like this, that makes sure that the heat is evenly distributed throughout the ship, throughout the engine, okay? And but I can't tell you how long from a cold engine you would do before you would be happy to slug it with steam. What I think you would do is you got to have the boiler running. Let's face it, you got to have the steam from a boiler and heat her up first. That's all I can say. So starting up a cold ship starts with that little engine there, putting kerosene into one of these boilers.
See, there's a YouTube video he found there's a triple expansion steam engine in London, in England, that pumps water. They showed it, they got a little steam engine that's rotating it to get it started.
I would say that if you want to see reciprocating steam engines in operation, there's a Liberty ship on both the East Coast and the West Coast that will take you to sea for a day. I think it's about 150 a head, and they treat you royally, they feed you well, and you can go down in that engine room and you can watch that clunker go around. Now, a triple expansion engine on a Liberty ship provides maybe 1/10 the horsepower that the ones on here provided. But they only went 10 knots.
Folks, we are gonna have to move on.